Welcome to Study Loop.
This is chapter 27, problem number 6. We are given an electron moving through a region where there is an external magnetic field. We are asked to calculate the minimum acceleration and maximum acceleration that the electron can have in part A. In part B, we're given some information about the actual acceleration, and we're trying to calculate the angle between the velocity vector and the magnetic field vector. So let's start with part A. As we know, the magnetic force equals to QVB, sine of the angle between V and B vectors. From Newton's second law, it's going to be equal to m times a. So if we want to get an expression for acceleration, we can divide both sides by m here. QVB sine theta divided by m then is going to give us the acceleration. So now if you want to find the minimum acceleration, we would look at the sine function where it becomes minimum. So if we have theta as 0, sine of 0 would give us 0. Therefore, if we plug that in here, we're going to figure out that the minimum acceleration that the particle can have is actually 0. And this only happens when velocity vector is parallel to the magnetic field vector, so that the angle between them would be 0. Given the same logic, if we want to find the maximum acceleration the particle can have, we're going to look at the sine function where it becomes maximum. If the angle is 90 degrees, then sine 90 gives you 1, which is the maximum value for the sine function. Again, then a max, the maximum acceleration, would become QVB over mass of the electron. So if we use this expression and plug in the numbers, we can find what the maximum acceleration is. So the charge of an electron is 1.6. The magnitude of it is 1.6 times 10 to the power of negative 19 coulombs. And then we have the speed, 1.4 times 10 to the power of 6 meters per second. And then we have the magnetic field, 7.4 times 10 to the power of negative 2 Teslas, divided by the mass of one electron, which is 9.11 times 10 to the power of negative 31 kilograms. When we plug everything in this expression, we get 1.82 times 10 to the power of 16 meters per second square as the maximum acceleration of the electron. Now in part B, let's go on the page. Part B, we are given that information. The actual acceleration in part B is given to us as 1/4 of the maximum acceleration that we calculated previously. So let's write that information down, and let's write the expression for the acceleration. We said that it was QVB sine of the angle between V and B. Let's not call it theta again. Let's call it theta prime, because we know that this is a different angle, divided by the mass. Now we're given this acceleration, but we're asked what the angle is, so we want to isolate this term out of this expression. So then sine theta prime is going to be mass times the actual acceleration divided by QVB. But we want to write this in terms of the maximum acceleration. So A is a max over 4. Then we're going to have m times a max over 4 QVB. And if we plug in all the values that are given to us, the mass is 9.11 times 10 to the power of negative 31 kilograms. And A max we found out to be 1.82 times 10 to the power of 16 meters per second square over 4 times 1.6 times 10 to the power of negative 19 coulombs times the velocity is 1.4 times 10 to the power of 6 meters per second. And the magnitude of the magnetic field is 7.4 times 10 to the power of negative 2 Teslas. Please add the coulombs here, capital C. So then when we do this calculation, we're going to find sine theta prime to be 0.25. So when we take the inverse then of the sine 0.25, we get the theta prime to be 14.5 degrees.